Hey folks, welcome to our module on binary search trees. So in this module, what we're going to be discussing is an implementation for symbol tables. So symbol tables were introduced in the last module. The idea of a symbol table is to have this generic data structure where I can basically have this idea of key value pairs, where my keys, instead of being something simple like an integer, something like an array might require, we allow them to be anything. And what we did in that previous module was we had a couple of approaches. We talked about using lists, we talked about using arrays, and that was okay, but the performance was a little bit weak. So what we want to do now is basically try a different approach. We're going to try a different data structure, right, a binary search tree, and try to get better performance. So in the following videos, basically what we're doing is we're going to go through and introduce the concept of binary search trees, and then spend a whole lot of time actually implementing them, right, and going through basically using a BST, right, to implement all the different functions inside of an ordered symbol table, which would be a little bit nice. Well, it'll be nice, right, because that's basically all the functionality. Sometimes, right, when we're implementing these things, it's like, well, it's hard for me to implement the ordered stuff. I can only do a simple symbol table, right? That can be annoying sometimes. Here, we're actually going to be able to get everything. All right, so the first thing we want to talk about is basically the concept of a binary search tree. So this kind of relates back to the idea we saw in our section on priority queues. So in priority queues, right, we basically introduced this idea of a heap. So a heap was a data structure. We had this rule where we said we have these different nodes, and then these nodes, right, form a binary tree. And this binary tree, and this heap, right, this binary tree, had some rules about how things could be structured. It said basically that if we had something called a max heap or max priority queue, the nodes on top had to be larger than the ones below it. Okay, we had that basic rule. And so now we're introducing binary search trees. There's something that's a little bit the same there, right? It's still a binary tree, right? It still has this basically the situation where every node has at most two children. But now we're going to change the rules just a little bit. Okay, so instead of having this top-down order rule, we're going to have a left-to-right rule. All right. So let's just take a look at the left. In this picture here, basically we have a heap. This thing over here is a heap. And if we look at it, what we'll find out is that the heap property, right, of top node is larger than the bottom one, is satisfied at every point. Since over here, right, 10 is larger than 7 and 8, 7 is larger than 2 and 5. So that's definitely a heap. And somehow, right, the flow here is we have, largest, is on the top. So this is large to small, basically how the tree will look. On the right-hand side, we have a binary search tree. And you may have seen these before. In the prerequisite class, right, if you took, your second semester Java, they may have introduced these. So you may have a little bit of idea of how they work. Again, right, we have this idea of nodes. We have this idea of children of this of nodes, right? We start at the root, right, go down. Looks a whole lot like a tree, like a heap. But now, right, we have a different rule. So our rule, right, we can already tell it's different because we see things like, for example, our 8 and our 10 are flipped. Our rule here, right, is basically that we have smallest on the left-hand side and largest on the right-hand side. So this, right, is basically going to the largest over here versus this is going to the largest over here. So our ordering is a little bit different. You can see, right, so I have my differences here, right? So 8 and 10, some are different. 5 and 7 are different as well. So in this case, right, we basically see that even though we store in the same data, the data is organized a little bit differently. And this different way that we're storing it is actually going to make it easier for me to find elements in it. Hence, they're called binary search trees, right? This order makes it easy for us to search for specific elements. In terms of a heap, heaps are optimized for finding what is the largest element, right, or what is the smallest element. They only really cared about one specific thing. Here on BST, we want to be able to find anything with relative ease. Note that in the future, though, we basically will have to kind of pay a cost for this. In terms of heap, right, heap was basically, it's really restricted. We only look at that one element at a time. It's also, though, rather, easy to implement, right, rather fast as well. For BST, right, not so much, right? It's going to be a little more complicated to implement. It's going to be a little bit, mainly it's going to be more complicated to implement. And our times will be, they'll be close to heap. They'll be basically the same big O class, but they're a little bit worse, right? If you forget about the big O class, it's a little bit worse. But anyways, yeah. So we're going to be talking about BSTs in this section, right, which have this kind of different order, and we'll have kind of a better diagram on the next slide. Here's a question for you guys, though, before we kind of move on. Are heaps BST? So is it correct to say that given a heap, it's a BST? Is that a correct thing to say? So no, right? I mean, we can look at this example right here. We have a heap. It's a legit heap, but clearly, if I try to make it a BST, I have a problem, right, because this thing is out of order. So clearly, that's not the case. Probably, right, the only time you're going to have a heap that is a BST is when you have something that's like, it's like one element, right, or two elements. It's very, very short, right? There's no need to kind of put stuff over here. That's where you get into trouble, because a heap basically you have to fill it on top to bottom, left to right. As you start to fill in, you kind of are going to end up running. You kind of end up in the scenario where you're putting something here that is actually smaller than this rather than larger than it, right? So if you kind of go past 2 elements, you're probably not going to have anything that looks like a BST. So in general, no. What about the other way? Are BSTs heaps? So again, the answer is no, right? So this is another thing that's going to be, well, it's less distinct. But here, right, you can just again look at your picture, right? Our largest is on the right-hand side, it's not on the top, clearly not a heap. There is kind of one scenario where BSTs are heaps. And maybe actually what do you guys, so let's see if you can identify, right? So think to yourself, what type of BST could you have that would make it, a heap, right? What would that thing look like? So take 1 second to think about that. All right, so hopefully you thought about that for a few minutes. Basically, right, it's this one over here. So we'll go 10, 8, 7, 5. So if I have a tree that basically just goes down the left all the way, that's a heap, right? Well, it's a heap, but it's not a complete heap, right? It's following the heap ordering, but I don't have this stuff filled in over here. So this is the only way I could even get that heap rule to be satisfied, right? That top-bottom rule to be satisfied. Non-general, right? You're basically going to say these things are distinct, right? They're always different, right? Heaps and BSTs are distinct things, right? That's kind of where our takeaway is going to be here. There's not a whole lot of overlap just because of the way the largest element is forced to be at different positions in these different structures. All right. So just a random note here, which kind of doesn't belong on the slide, but we need to talk about it. Is that when we go in and we actually implement these later, right? We'll do these in a few videos. Our idea, right, our requirement, right, that a simple table can basically only store one value with one key, or can only store one value with one key, will actually help us out. What we actually basically get is the ability to ignore the chance of having to deal with duplicate keys, right? Duplicate keys will give us an issue, right? So drawing a BST, and you can imagine, say I have another 8 in this one over here, right? Imagine I was trying to add this node. All of a sudden I get confused. Does it belong here? Does it belong here? Right? I have to add some additional rules. That would be a lot of work to deal with. But for us, right, what we're basically going to say is that can never happen. Together with that, I guess I have to mention to you guys, these numbers on the nodes here, these are keys, right? So when I have that 8, 10, 5, 2, 7, those are intended to be keys. I'm generally not going to draw the value when I do BSTs, right? You just have to kind of know that, hey, there's a key value pairing, right? And I'm just looking at that top as being this is the current key, right? Because that's what I care about. That's what controls the order in the structure. So yeah, I don't have to care about duplicate keys, so it'll make life easier for me later on. So that's just a side requirement there. All right, so talking a little bit more about these definitions of these things, right? So we have, right, this idea of a binary tree, right? You guys know this, right? It's a tree where, every node has at most 2 children. Then a binary search tree. So here's kind of our formal definition here. We're going to do another definition on the next slide as well. Basically, our binary search tree, right, is a binary tree where each node's left child has a key less than the parent, and the right child has a key greater than the parent. Okay, so we're basically enforcing that left-right order, right? Left is smaller, right is larger. Okay. You can kind of see this in the picture over here, right? So it's like, for example, here, right, we pick on this node over here. This is node E, and we look at the left. Left is A. Well, A in alphabetical order, that's less. Looks good. On the right-hand side is R, greater in alphabetical order. Again, we're good. So yeah, that's kind of our rule, right? If we look at our tree, right, that's what we expect to see, right? And you can check it if you want, right? I have the example from the previous slide here, right on the right-hand side, this thing over here. And if you look at all those nodes, right, you can basically see that left-right ordering holds. So let me see. Let me actually try adding a node really quick, and I'll ask you guys a question. So suppose I add the following. Is this a BST? Well, sure, right? 6 is less than 7, so that's good. What about if I add, let's say the number 3? Is that a BST? Sure, 3 is greater than 2, right? It's the right-hand child. As I draw through this, right, I need to really be certain I know what is the left side versus the right side. Because I could, right, imagine if I do this a little bit differently. I could draw this. All of a sudden what we're saying is that 3 is the left child of 2. Is this a BST? Well, no, it isn't, right? In this case, right, my rule has been broken, right? 3 is not less than 2, so this isn't a BST. So this, right, cannot occur, right? I have to put my 3 over here, right? I have to put it basically, next to on the right-hand side, right, of my 2. So yeah, right, now we get a valid BST. So basically, right, that rule kind of enforces where we can put elements. Elements have to go, at a certain position. I can't just arbitrarily add them to the tree, right? I have to, follow a certain ordering. All right. So one last thing to talk about is basically the recursive definition of a BST. So this is maybe an alternative to the one we talked about before. So we say that a node is the root of a BST if the left child is less than the parent, right? This is the rule from before, and the left child is the root of a BST, right? Second bullet point, right? A right child is well, the right part of the definition is basically, a right child has a key greater than the parent, and the right child is the root of a BST. So somehow, right, what we're adding is the following, right? This is kind of our extension of what we were talking about on the previous slide. Is we're going to say that not only do those rules hold for left and right, right? Smaller things on the left, larger things on the right. But in addition to that, right, the full definition should have that the left side is a BST and the right side is a BST. It's sort of implied in the previous one. Here we're just making it explicit, right? So BSTs are built from BSTs, right? And so if you look at this example here, right, what you can actually kind of see is that I have, right, so this is basically a node over here with a BST on the left side and another BST on the left side. And I don't know how to try this in without making it look bad. Okay, another BST over there, right? This over here inside, right, is a node plus, right, a BST and a BST, right? This is a node plus a little BST and a little BST, okay? So basically, BSTs are built from BSTs with the left and right sides, defined with that certain rule. So a lot of times, right, when you introduce recursion, right, people think, so what, right? Why do we care about this, right? What does this actually give me? Well, it gives me something very strong or something very powerful, which is, it's a recursive data structure. That means we can use recursive methods, right? And so when we go and actually implement this data structure, what we're going to have doing again and again and again is just constructing recursive functions, right? Recursive methods. We're going to have methods that call themselves, because we already know, right, trees are built from trees. So it's like, oh, I have a function, I'll call it on the root, and then the root will call it on the left and the right subchildren. So we're going to basically be able to kind of deal with a lot of complexity of this branching tree by just writing our methods in terms of recursion, right? And it's a very natural thing to do because the data structure itself, right, this tree data structure, it is recursive. When we talked about priority queues, right, we didn't need to use recursion, right? We just, we had our heaps, right? In our heaps, we had loops to go through them. That was fine. Here, right, because we're doing a little bit more complexity, right, it actually makes sense for us to do it using recursion, right? It makes sense for us, right? The structure is recursive, right? So we'll try to utilize that the best we can. So when we go through these different kind of implementations of the different operations for a symbol table, you'll see it basically at every turn, right? Every single function will be recursive in some sense. And if you want, you can actually go and try writing them in terms of an iterative approach, right? Meaning not having any recursion. And what you'll actually find out is it's a very difficult task. There's all sorts of extra variables you need to keep track of, all sorts of extra work you need to do. It's a very, very kind of complicated thing. So this will end up being very nice. All right, so that kind of gives you guys kind of a review, right, of the BST concept. In the next videos, we're talking about a little bit about we'll talk about how to basically traverse a tree, right? How to basically visit all the different nodes in it. And then from that, right, we can kind of go to our main chunk of material for this module, which is the actual implementation of this data structure.